In high-volume manufacturing, a part can pass quality control and still shut down an assembly line. This high-precision pin measures perfectly to its specified diameter, but when it meets the mounting bracket, it binds against the rim and stops dead. A digital protractor reveals the physical interference. The hole is drilled at an angle of exactly 89.2 degrees instead of a perfect 90. The diameter of a hole, its size, does not control its angle, its orientation. You can manufacture 1,000,000 parts with perfect diameters, and if the orientation is ignored, none of them will fit together. Engineers solve this ambiguity using a specific geometric control. In GD&T, it is represented by an upside-down T inside a feature control frame. The ASME Y114.5 standard defines the symbol as perpendicularity. It dictates that a feature, whether a flat surface or a cylindrical axis, must remain at exactly 90 degrees relative to a specified datum. Perfect right angles only exist in CAD software. Perpendicularity bridges that mathematical ideal with the physical reality of machining, giving the drill bit an exact boundary for its acceptable drift. Without this explicit control, assembly fit becomes a matter of probability. Leaving orientation up to chance risks millions of dollars in scrapped parts and machine downtime. On the shop floor, machinists often confuse the required tolerancing for a surface. Flatness, parallelism, and perpendicularity are treated interchangeably, but they dictate entirely different physical constraints. Flatness is a form control. It requires no datum. As this diagram shows, it only governs how wavy a single surface can be in isolation, trapping the material between two floating parallel planes. Parallelism introduces an anchor. Here, the two transparent planes are locked perfectly horizontal relative to a highlighted base, known as datum A. The surface must be flat, but it must also maintain a 0-degree relationship to that base. Perpendicularity operates on the exact same logic, rotated. The tolerance zone now stands at a perfect right angle, rigidly locked to datum A. While perpendicularity implicitly forces a surface to be flat within the specified limit, its primary job is maintaining that 90-degree relationship to the anchor point. Because it defines a relationship between two features, a perpendicularity control is mathematically invalid unless it references a specific datum. Swapping a form control for an orientation control alters the entire manufacturing workflow. It dictates how the part is clamped in the mill and what instruments the inspector pulls from the tool crib. Translating surface perpendicularity from an engineering drawing to a physical piece of metal requires understanding the exact shape of the tolerance zone. The 2D drawing specifies a 3D volume. A 0.1 mm perpendicularity callout creates a planar tolerance zone, two vertical planes exactly 0.1 mm apart. The surface can wobble, provided it stays within these rigid boundaries, which are anchored at exactly 90 degrees to the datum. This geometric constraint ensures that mating surfaces sit flush. It prevents the leaning edges that cause gaps, vibration, or severe physical interference in a bracket assembly. When the design moves from flat surfaces to cylindrical features, like mounting holes or alignment pins, the geometry of the tolerance zone changes. Controlling an axis requires a 3D cylinder rather than two planes. This transparent vertical cylinder is the absolute boundary for the hole's orientation. Inside is the derived median line. This jagged path represents the true, mathematically calculated centerline of the actual drilled hole. For the part to pass inspection, the entirety of that derived median line must fall inside the cylindrical tolerance zone, anchored rigidly at 90 degrees to the datum. The stakes for axis perpendicularity scale with the mechanical load. Consider an engine block, where the cylinder bores must align precisely with the crankcase stack. A fractional tilt causes severe misalignment. The piston generates extreme heat and friction against the cylinder wall, leading directly to premature wear and engine seizure. Axis perpendicularity forces the machining center to maintain precise alignment, ensuring that rotating and sliding components operate without binding under heavy stress. Applying the correct symbol on a drawing is only half the process. Those tolerances must be verified physically on the shop floor. For surface perpendicularity, inspectors rely on manual methods. They secure the datum against a granite plate and measure the vertical face with a precision square and a dial indicator. Axis perpendicularity demands digital precision. A coordinate measuring machine uses a ruby probe to map points inside the bore, calculating the invisible centerline's exact orientation. The required inspection method changes completely if the engineer applies a maximum material condition, or MMC, modifier to the feature control frame. MMC allows the use of a functional gauge. Instead of mathematically calculating a centerline, an inspector simply slides a perfectly manufactured steel go pin through the hole. If it clears the block, the orientation is within the allowable limits for assembly. The transition from a slow, precise CMM to a rapid hard gauge demonstrates why the inspection protocol must perfectly match the modifiers written into the original drawing. We can now return to the failed assembly line and correct the initial engineering oversight. The revised drawing includes a feature control frame, applying a perpendicularity symbol and a 0.2 mm tolerance to the mounting hole relative to the bottom face. This explicit instruction forces the machinist to tram the drill spindle, squaring it perfectly to the primary datum before making the first cut. The resulting part accepts the high-precision pin instantly, sliding smoothly into place with zero resistance, allowing the entire factory assembly line to move forward. The principles are strict. Perpendicularity always requires a datum. It projects either a planar or cylindrical tolerance zone, and it is the strict mathematical control that guarantees reliable assembly. Mastering these orientation controls ensures your geometry survives the transition from digital model to physical object. Next lesson, angularity, controlling features at any specified angle.